Okay, so now that we have clear the core for Bayesian inference, let's talk about the extensions. More concretely, the extensions for this Bayesian approach. So, quick recap. Now we have probability assumed as the expression of a belief. We have prior beliefs that the model without knowing the data, and also posterior beliefs that the model knowing the data. And to obtain these posterior beliefs, we need data to obtain the likelihood and the specifying of prior beliefs on the model. And so we need to be rigorous and explicit about our beliefs in the model. Therefore, we will combine in our minds these prior and likelihood elements towards a posterior distribution that can be expressed as posterior distribution is likelihood times prior divided by evidence. So we have these examples with discrete and continuous variables, and also these examples of prior and posterior. So now we don't have point estimates like p-values, but the entire posterior distributions to describe. So the inference is more complex, but also is enriched because we can have some things that normally we cannot do with NHST. For example, the prior-posterior analysis are also the highest density intervals that are analogous of confidence intervals, but in my opinion better. We also have bias factors that are kind of p-values, but in my opinion better and more informative. And we also have some things that you cannot get into in NHST, like sequential analysis and also robustness analysis. The prior-posterior analysis is basically plotting or describing the prior distribution and the posterior distribution and see how much the data likelihood is impacting these states of belief. So we can search for difference in position. So for example, if the expected value is in another place, we can also search for differences in dispersion and position. For example, here we will have a prior that had a much greater variance than the posterior because it's way more platycortic, and the posterior is way more narrow. And also the expected value here is different from the posterior. So we can also search for differences in position and also in dispersion. But also we can even encounter differences in form, position, and dispersion. For example, here we'll have a prior that only assumed positive values. Then the posterior will have a different form, a different position, and a different dispersion. This is meaningful. For example, data has been very impactful because we have a modest prior with only positive values, and then data likelihood has been very certain because the dispersion is way smaller and it's everything more narrow. And also, it's not actually around zero, but way more to the right. And also, the form has changed because now it's not like a huge cut point in zero, but the probability of have this effect size in zero starts increasing to get to a reach point and then get down. Okay, the next thing is our highest density intervals. They are also called credibility intervals, and that analogous to the 95% confidence intervals. So these intervals of the posterior are rounding the expected value, and the probability in them is credibility. Normally it's specified as 0.95, and it's basically having a specific area of the posterior around the expected value. So you can have 95%, 90%, 99% is basically up to you, normally with a high probability. The most of the area of the posterior is encapsulated in that interval. Okay, so the interpretation becomes more intuitive. For example, a non-overlap with a threshold or the expected value of the prior or with another HDI implies notable differences because if it doesn't become overlapping, then we can assume that the posterior distributions are basically in another place, and that's meaningful and that's okay. And the interpretation is more intuitive. The probability of this posterior is higher or lower in the vast majority of the distribution than this threshold or this other distribution, and that's it. We don't need these complex intervals, confidence intervals interpretations, like if we draw 100 random intervals, then 95 will contain the parameter, so we don't know if our specific interval is one of them, but we will assume that. So that complex interpretation of confidence interval is erased, and it's actually, this is quite straightforward, which I think is an advantage. Okay, so these are specific examples of the highest density intervals. Here we have symmetric HDIs, but we also can have asymmetric HDIs with the expected value not in the exact middle of the two intervals, the bounds of the interval. And also we can have more complex things. For example, if we have bimodal distributions, we can customize the HDI to be, for example, two places at the same time. The important thing is that they encapsulate 95% of the distribution. Okay, there are other type of intervals, for example, the equally tailed interval or ETI, but normally the HDI is the common practice. Okay. The next expansion or extension to Bayesian inference is called bias factors, or BFs. Normally in NHST we have the Neyman-Pearson lemma that is called H0 and H1, but normally we don't work with H1. However, if we want to explore both H0 and H1, we need to model both of them from a Bayesian perspective and then compare them. So now we can have a posterior distribution of H1, that is basically the likelihood under H1, multiplying the prior of H1 and the marginal likelihood of the whole scenario. But also we can divide it of a posterior distribution of H0, that is the likelihood or data likelihood under H0 multiplied by the prior of H0 and the exact same marginal likelihood of the scenario. Therefore, all of these complicated members will become one, so they can be just simplified, but also we have very interesting things. The posterior odds and the prior odds will have a bias factor with them. This is called the bias factor, the quotient or the ratio between likelihoods under H1 or H0, and this will be multiplying the prior odds to obtain the posterior odds. Therefore, it's a factor, it's something multiplying something. More concretely, the bias factor is multiplying the prior odds. It's not the posterior odds like this, it's the prior odds. And it's a ratio, it's a quotient of probabilities. Therefore, it's really useful to have that, because we can have two types. Bias factor 1,0, that is H1 against H0, indicates the evidence for presence of an effect, and bias factor 0,1, that is H0 versus H1. This is the evidence for the absence of an effect. And it's basically the same thing, so one is the inverse of the other. Normally it's bias factor 1,0, the normally used. And we can have such nice things, for example, like this, that they are called pizza plots. And we can allow them to continuous interpretation. So if we have a bias factor that is basically 1, we will have equal probabilities favoring H0 and H1. As long as this number increases towards infinity, for example 3, 10, 30, 100, 1000, whatever, the evidence for H1 is going to be stronger and stronger. Remember that if you switch them to bias factor 0,1, it's going to be the other way around, so don't get confused. Regarding bias factors 1,0, as long as this number is greater and greater and greater, the degree of evidence favoring H1 is going to be greater and greater. So we can define some sums. For example, weak evidence is going to be bias factor between 1 and 3, but more or less 7, 8, 10 is going to be moderate evidence. And then we will have strong evidence towards 20 or higher, and also we can have strong evidence towards 100 or something like that, on way ahead of 100, 150. We can call it extreme evidence. This thing happens in a specular way, like in the other way around, between 0 and 1. 1 out of 3, 1 out of 10, 1 out of 30, 1 out of 100, 1 out of 150, or whatever you want. It's indicating the evidence favoring H0. So we have 3 things that we can interpret in this continuum. The evidence favoring H1 the evidence favoring H0, and also this area in between that is inconclusive evidence or weak or negligible evidence towards one of the hypotheses. So we can conclude basically three things. We can conclude for support for H1, support for H0, or inconclusive evidence and we need more studies. Okay, so this is Bayes factor, a very cool thing to have, and we will move forward on the next video.